Now let's have a discussion on how we go about multiplying fractions. But first, let's recall one of the topics we mentioned a second ago. We've actually sort of brushed against this topic in our previous examples when we talked about how to, say, convert some fraction a over b using the equivalent properties, the equivalent fractions property. We said that we can create a new fraction by multiplication of the numerator and denominator by some constant term, right? Well, it turns out we can basically extend this idea generally to how we multiply fractions. So in the case that you see here, I am multiplying the fraction a over b times a second fraction that happens to be a constant over itself, right? So we mentioned that a constant over itself is always 1, but ultimately we get as a result this sort of computation where we multiply the numerator values together and the denominator values together. So generally speaking, that's how we can multiply fractions. So here's a visualization to give us an example. And again, generally speaking, you can see how the multiplication is performed. If I have two fractions, here represented as a over b times c over d, we can just multiply numerator values together and divide by those denominator values multiplied together. So my first visualization here, if I look at the number of blocks, in total there are 4, 3 of which being shaded, I can show this as a fraction 3/4, right? So notice that in words here we say that we're going to take half of 3/4. This suggests that we're going to do some multiplication, right? So if I multiply those two fractions together, again, according to this generalized format, I have 1/2 times 3/4. And so multiplying the numerator values, I get 1 times 3 is 3. 2 times 4 is 8. And so you can see the visualization here, the gradated portion, we have 3 now, though, out of 8 total equal parts, right? So the gradation there illustrates the solution to that multiplication. So let's look at some more examples. Generally speaking, when you do multiplication, you won't always get a nice simplified fraction like this. In the case that we have here, we're asked to multiply the fraction -9/20 times 5/12. And I want to mention that because the fractions are not always going to result, especially when we multiply or divide, in some simplified fraction, we actually do need to continue using that equivalent fractions property to further reduce a problem. And there's a couple of ways to go about that. So let's look at the example we have here. Again, I have -9/20 times 5/12, right? And my general fractions multiplication looks something like this. We got a times c in the numerator as the result, and b times d in the denominator, right? So just following that, I would have here as my solution, since I have a negative value times a positive fraction, I'll have a negative solution. In the numerator, I have 9 times 5, and in the denominator, I have 20 times 12. Okay, so now this is technically the solution. It's not simplified by any means. We just sort of put it in the correct format. But here's why I want to approach it in this way. Instead of doing the computation 9 times 5, and then figuring out what 20 times 12 is, and trying to reduce that new fraction, what we'd like to do is just consider if there are any common factors in these smaller values before we do that type of computation. So for instance, I could say that 5 and 20 have common factors of 5, and that 9 and 12 would have common factors of 3. So let's rewrite each of the terms such that we can sort of pull out those common factors. So again, my answer here would be negative ultimately. And the fraction I want to rewrite as, in the numerator at least, 9 becomes 3 times 3. And we still have multiplication by 5 there. 20, however, we want to rewrite as 4 times 5. And 12 we would like to rewrite again as 4 times 3. So I've basically broken these down, not quite to their prime values, but I've broken the larger numbers, these composite numbers, into smaller chunks so that I can see the common factors that are going to cancel. So the 3 and 3 in numerator and denominator will cancel, so will our 5's here. And so ultimately what I'm left with in the numerator is just, again, my fraction is going to be negative. I have a 3 there, and then in the denominator I have 4 times 4 is 16. So negative 3/16 will actually be the simplest version of this problem. Now, if you have a calculator, it's fairly easy to crank this out, but since we don't always have that available to us, it's nice to be able to use this technique because you can break these composite numbers into their component parts without having to do loads of computation. And that's the sort of skill set that would allow you to get through a problem much more quickly. So let's take another look. This is another example where we're doing multiplication by some fraction, but instead of another fraction as our multiplier, we have some whole number value. In fact, the expression negative 9a doesn't look anything like a fraction. So how do we actually approach a problem in this way? So what it requires is that we recognize that we can create fractions of whole numbers. All we have to do is put that value over 1 to create the fraction. So for instance here, I would start by restating the initial fraction, and I could say this is multiplication by the fraction negative 9a over 1, where now it's clear that I still have multiplication of fractions. Putting negative 9a over 1 doesn't change the value, but it does create a fraction so that I can sort of remind myself how this calculation is done. So just as before, I'll just simply put the numerator terms together. Yet again, I have a negative and a positive term being multiplied, so my answer should be negative. In the numerator, I would get 11 times 9a. And in my denominator, I get 3 times 1. So I'll just write that as 3 for the time being. So before I make any sort of computation, yet again, I could consider, are there any terms here that have common factors? And in fact, 9 and 3 would be two terms that do have common factors. So I could, for instance, here say that 9 breaks down into 3 times 3. I still have my variable term a in there. And division by 3 in the bottom lets me know that at least one of these 3's is going to cancel. And so ultimately I get the result here of negative 11 times 3, which is negative 33, times a. So negative 33, 80, and it looks something like this. And since 3 divided by 3 gives me 1, my denominator just sort of phases out. And I'm left with the solution here, negative 33a. So if you do encounter some of these whole number values, just remember that you can always put that whole number over 1 and reinterpret this again as just multiplication of fractions. So now let's look at another topic on division of fractions. How is division of fractions associated with these types of computations? So before we get into division of fractions, we need a new concept, one that's called the reciprocal. So if I have some fraction and we use our generalized version, that's a over b, we say that the reciprocal of a fraction a over b is just b over a. So we exchange the numerator denominators, essentially switching their locations, right? And it's described more precisely by this relationship. When I multiply a fraction by its reciprocal, I always get 1, right? So looking at my 3 examples here, what would be the reciprocal of a whole number like 10? Well, we mentioned that you can create a fraction using division by 1 if I have some whole number value. So the reciprocal of 10 over 1, if I interpret it as this fraction 10 over 1, I can then find the reciprocal by exchanging that numerator and denominator value. So the reciprocal of 10 is 1/10. For part B, the reciprocal here would be exchange of the numerator and denominator. It still remains negative. My reciprocal here would be negative 6/5. For part C, I start with a fraction 1/2. The reciprocal here would flip that and give me 2 over 1, or I could just write it as a positive whole number 2, like this. So this reciprocal idea is one that's fairly simple to figure out. It's helpful for division in the following way. When we define our fraction division, as you see in the generalized form here, we actually convert back to a multiplication type operation. So if I have two fractions, say a over b divided by c over d, that is the same as multiplication by that reciprocal of the second term. So notice that my second term becomes multiplied, that d over c now, right? The exchange of the numerator and denominator values occurs when I change the operation to multiplication. Why do we want to change it to multiplication? Well, we already know how to multiply fractions. It's fairly straightforward. We multiply numerator times numerator, denominator times denominator. So ultimately, fraction division becomes multiplication by the reciprocal of the second term. So let's look at some examples. So here we're asked to divide the fraction negative 2/3 by n over 5, right? So again, negative 2/3 divided by n over 5 looks something like this. And we want to create an equivalent statement, but in terms of multiplication by the reciprocal of that second term, right? So again, we have the first term written as is, but now we want to find multiplication by the reciprocal, right? So what is the reciprocal of n over 5? Well, we exchange that numerator and denominator value, we should get 5 over n. And now we can make our computation. So here I get a negative fraction times a positive fraction is going to be a negative result. In the numerator, I get 2 times 5 is 10. And in the denominator, I get 3 times n is 3n, like this. Now, there are no common factors here, so I don't need to simplify. This is going to be our solution, negative 10 over 3n. So let's look at one more example. Here I'm asked to divide the following fractions. I have negative 7/8 divided by negative 14/27. So again, I will just restate the problem here. Negative 7/8 divided by negative 14 over 27. And we can rewrite this in terms of multiplication, again, by the reciprocal of that second term, right? So I'll restate the first. We have negative 7/8 now. We want to multiply, however, by the reciprocal of negative 14/27. So the reciprocal there would be still negative, but now it's 27 over 14, like this, right? So unlike the previous example, we actually have some larger values that would need to be computed here. And so instead of multiplying, say, for instance, 7 times 27, coming up with that value, and then dividing by whatever 8 times 14 happens to be, we could approach it in the following way. So first I'll note the sign of my solution should actually be positive, right? Since I'm multiplying a negative times a negative value here, my result should be positive. And just sort of putting the terms together in the numerator and denominator, it looks something like this for our result. At this stage, I'm going to consider, are there any ways to reduce the terms such that I find those common factors? And in fact, easy one to see here is that 7 and 14, let's say, have a common factor of 7. And so I can simplify somewhat and say, well, 7 and 14 could be rewritten slightly differently. 14, for instance, could be written as 7 times 2. 27 and 8 also have common factors. In this case, I could say that 27 is the same as 7 times 4, and 8 is just 4 times 2. Right? So we've introduced all the appropriate factors that will help us reduce this really quickly. So top and bottom values that are going to cancel are the 7s as well, the 4s here. So what am I left with in the numerator? Well, I have 7 left, and in the denominator I have 2 times 2, so 7/4 would ultimately be my solution here, and it is a positive value. So now let's talk about how to use the techniques that we've talked about here so far to simplify some expressions written with some fraction bar to create what look like complex fractions, right? So generally speaking, if you're asked to simplify some fraction bar expression, you can approach it by sort of isolating the numerator on its own and then the denominator on its own before making the final computation. one other thing I should mention here is also the placement of the negative sign in fractions like these. You'll notice that I have three equivalent statements here, all of which have some negative sign, right? So I can attribute the negative sign to the entire fraction, right, which is the case in the last frame here. So negative a over b is where I'm saying I have some negative fraction, right? But I could also associate that negative sign with either the numerator or denominator separately. And so you'll see that that is the case and can be done so in these examples. So here I'm asked to simplify the following. I have 3 minus 5 in the numerator, 7 plus 1 in the denominator. Given the numerator values here result in a negative integer value, I could say 3 minus 5 is negative 2, and 7 plus 1 gives me positive 8, right? So now the integer value in the numerator is the one that is being associated with the negative sign, but if I sort of drag it out front here, well, now it's negative 2/8. Subtle difference there, but it doesn't change the outcome. I still need to simplify this expression exactly because there's a common factor between the numerator and denominator. It happens to be that 2 and 8 have a common factor of 2. So if I divide 2 by 2, I get 1, and 8 divided by 2 gives me 4. So negative 1/4 is the true simplified version for this example. So let's look at another with a few more operations involved. Let's say I want to simplify the following. Again, I want to separate, at least computationally, the expression in the numerator and denominator, right? So if I just look at the numerator for a moment, the numerator here I have 4 minus 2 times 3. And for my denominator, I'm focused on just finding what 2 squared plus 2 is, right? Before we actually do the division. So 4 minus 2 times 3, that hierarchy of operations, the order of operations, PEMDAS, lets us know that we need to multiply 2 times 3 here first and get 6. 4 minus 6 results in the integer value negative 2. For my denominator, I have an exponential there, so 2 squared is what I should perform the operation on first. 2 squared is 4, plus 2 gives me 6. And again, I can reduce and recognize that each of these terms has a common factor of 2. So I reduce by division. 2 divided by 2 is 1. 6 divided by 2 is 3. So I get negative 1/3 for my result here. Let's practice one more of these and take a look at the example we have here. Now we have another simplified question. We want to simplify this fraction. So focusing in on one piece at a time, my numerator value here, I have 4 times negative 3 plus 6 times negative 2, so several operations going on there. For my denominator, I have negative 3 times positive 2, and then we subtract 2. So just looking at that numerator, I have 4 times negative 3 is negative 12, and positive 6 times negative 2 gives me negative 12 as well. For the denominator, I would have negative 3 times 2 is negative 6, and subtracting 2, I can now simplify my numerator and denominator values to be one particular value in either one. So for the numerator, I have negative 12 minus 12. That is the same as negative 12 plus negative 12. That results in negative 24. And you'll notice that my denominator value also results in a negative integer. Negative 6 minus 2, or negative 6 plus negative 2, gives me negative 8. So it happens to be that I have some negative integer divided by another negative integer. That means my result should be a positive value, right? So in fact, when I do the result here, I get that 24 and 8 have common factors. If I divide each by for instance here, 3 gets my result, right? So 24 actually divides evenly into 8 parts. I get 3, a positive integer value for the result. So again, focusing on numerator and denominator separately, and then making your computation at this point will be the best way to go about these order of operation problems. So now we'll talk about the next section here on the addition and subtraction of fractions.